Okay, this is part 5 of our game theory lecture, the final section that we will go through, um, talking about games where we have actions available to the players that are continuous rather than being discrete choices, such as high, low, or medium price, or something like that, right? Or confess or stay quiet. Now we're thinking about being able to choose from a continuum of options, right? Which, right, if at this point you've been thinking that this seems, how is it related to our econ principles that we've been going through to be talking about all these obscure and sometimes bizarre hypotheticals, we are setting the tools and the framework really for what we're doing next week with oligopoly and 2 or 3 firms interacting with one another strategically to maximize their own profits, right? The players are the firms, the profits are the benefits that they receive, and their actions choosing their output level affects not just their own profits, but the profits of the other firms in that market. So we will here do one last hypothetical, which is essentially an auction game, which is the last section of the chapter in your book. And the setting I have prepped here for us is that we have, say, $10 million in economic rents to be distributed by a politician. Now, normally I would think of those economic rents as something like oil leases for oil drilling, where essentially you're just pulling excess oil out of the ground. Those are what we call economic rents. Sorry, not pulling excess oil, pulling excess net value straight out of the ground, right? Greater than the costs of extracting it. And so their economic rents are just sitting there waiting for someone to take them, as long as the government grants them the rights to do so. Here, let's be a little bit more contemporary and think of the $10 million as a portion of the $500 billion corporate $500 billion in corporate bailout funds that Congress just made available. So we've got this politician with $10 million that he can sort of spread around, and you have 2 corporate financiers. We'll just limit it to the 2, right, who want access to that cash. And the politician sets the rules of the game here. It basically says he's going to divvy up the $10 million by the share of campaign contributions that each individual pitches in, right? So suppose I am corporate financier number 1 who wants some of that cash for my business ventures. And here is the way that we could think about my profits from that, right? I contribute some amount, X1, to the politician's campaign. It's going to cost me X1 to do so. But at the same time, I gain, right, based on the proportion of total contributions from myself and the other financier, right? I gain some piece of the total. I'm just using an A for award, that being equal to $10 million, but we can keep it general for now and just carry an A around, right? So how much will I choose to contribute here? Note, this is the exact setup of a strategic game. We have 2 individual players trying to get some benefit, and the net benefit that each one of us, receives is a function not just of our own actions that we take, but also the action of the other player. All right, and so rather than choosing between a couple of particular discrete output choices or something, right, and maximizing the profits that I get from that, the only difference here is now I'm choosing from any particular contribution level, right? I could contribute as much as I want. Now, obviously, it should be, at the very least, upper bounded at $10 million, because I wouldn't contribute more than the maximum award, but I, in theory, could choose any value I like. How would I choose a value in a continuous variable to maximize this function? Same way we have been doing all this time with our calculus, right? I'm gonna take a derivative with respect to x1, d(pi1), dx1, and set that equal to 0, right? Now we've got a fun fraction here, so we got to use the quotient rule when we do this, but we get, that is going to be the derivative of the numerator times the denominator, right? So derivative of x1 is 1 times x1 plus x2 minus the derivative of the denominator times the numerator. The derivative of this x1 plus x2 with respect to x1 is just 1 times x1. That's going to be minus x1 up here, all divided by x1 plus x2 squared. The rest of that quotient rule. That's multiplied by a, and then minus 1, the derivative of that, and all that set equal to 0. All right, so that is that derivative that I'm going to use to get the profit maximizing x1 given whatever that possible value of x2 is, right? So first of all, got x1 plus x2 minus x1, so the x1s in the numerator go away, and I'm going to add a 1 to both sides, so I have x2 over x1 plus x2 squared times a is equal to 1, or x1 plus x2 squared is equal to x2 a, right? I'm just going to take the square root of both sides, because what I want is x1 as a function of x2 and a. Get my best response here. I get x1 plus x2 is equal to the square root of x2 square root of a. Okay, that's readable. And I can subtract the x2 over there to get x1 star, or equivalently, right? To put this in the notation that we started with, the best response for player 1 to any given value of x chosen by player 2 is going to be square root x2 square root a minus x2. Okay, so now here is where, first I want to stop and make sure we're thinking about this right, which is I want a Nash equilibrium. I want a point where both players are doing the best they can given what the other player is doing. So I need both players to be playing a best response like this. And what I also know is that the profit function that I set up here is identical for player 2, right? So, so I can allow here that x1 star and x2 star are going to be identical to one another in that Nash equilibrium, right? If you doubt that, you could reset up the same problem essentially, and solve for x2 star is equal to you will find that, right? And then you can plug one of these into the other, right, to show that x1 star, when you have x1 star and x2 star equal to these things at the same time, you'll get exactly what I'm going to find here. But I'm going to use the symmetry of this to shortcut my way through. In the equilibrium, x1 star is going to be equal to x2 star, and so I can just use an x star to denote what I'm looking at here. So I get 2 x star, right? Because x1 star equals x2 star equals x star. So it's x plus x is 2x is equal to x star, root of x star times a. Divide through by this root of x star, and I'll get a root on this side instead, and divide through by 2. So I get, sorry, I square both sides of that. 1/2 becomes 1/4. Square root of a becomes a. And both players playing their best response simultaneously means that each one of them will contribute 1/4 of the total award A, which in this case is $10 million. So both of them contribute 2.5 million for a total contribution of 5 million. That is the Nash equilibrium to this auction style game. So, although we've framed everything up to this point in terms of discrete actions that the players can choose, moving into next week, we will mostly be thinking about firms having continuous choice of their output level and maximizing profits in this competitive strategic setting between 2 or 3 firms. For the purposes of this course, I will not take us beyond 3 firms in the oligopoly setting, and we'll focus mostly on the duopoly setting of just 2 firms. And that is all for our game theory lectures. There are a ton of examples in the problems for this chapter. So if you're not feeling comfortable with these concepts, I strongly recommend going through and trying to solve a whole bunch of those questions in the back of this chapter, because there's lots of good practice there. All right, that's all for this week.